In this video, I decided to do something maybe a little unusual and give like a course outline of the type of mathematics that you can progress through to go from maybe a novice to something that you would see at the graduate school level. So this is sort of like the timeline that I think might be beneficial to some people. I'm not saying that this is the way to progress through mathematics, but this is like the path that I think a lot of people that study mathematics go through. And I've put in my own personal ideas of how the flow should go. Again, this is my own personal experience that I'm speaking of. Obviously, I'm not saying that this is the tried and true method, obviously, but these are just my thoughts, so let me know what you think. So first off, I'm trying to write and look through this camera at the same time. So the first thing you should start with is college algebra. And this is usually split up into 3 semester worths of material. So typically you would do like this in a fall semester, then a spring semester, then maybe a summer semester. And this class sometimes goes by different names. When I was an instructor at a community college, I taught a class called College Algebra 3. And in other places it's called trigonometry, other places call it advanced mathematics, other places call it pre-calculus. You know, it's not like it has its own specific name. But I'll call it College Algebra 3 here just because I like the 1, 2, 3. That's really the only reason. And then, so that's 1 year. And then the second year, I would go through calculus. Get you a nice calculus. Calculus. 1, 2, and 3. So there's typically 3 calculus courses. Calc 1 is kind of like the introduction to derivatives, how to differentiate, different techniques to differentiate. And then it may end with the antiderivative, which sets you up for Calculus 2, which is really all about integration and different methods of integration. And then they may talk about like polar coordinates. They might talk about conic sections. What else? How to find arc length of curves, but that's really just kind of integration, you know, the techniques used. And then Calculus 3 is usually denoted, or not denoted, but reserved for vector calculus, how to differentiate and integrate in multi-dimensional spaces, not just in the XY coordinate plane. And what else do they talk about? Partial derivatives, which is really what I just said. So vector calculus and that type of stuff. And usually there's like, they talk a little bit about ODEs, which stands for ordinary differential equations. But that kind of sets you up for the next class, which is what I'm going to put here. So at this point, you've kind of committed. These classes are usually recommended for non-math majors sometimes. Like, depending on your field of study, you may need to take all of college algebra. Maybe you only need the first 2. Some of the STEM courses will definitely have you go from Calc 1 to 2. Maybe not Calc 3. But after Calc 3, like if you go through Calc 3, you've kind of committed a little bit, I think, to either a degree in mathematics or engineering or something. So at this point, now you start taking multiple math classes in a single semester. So if you're doing like a self-study, this is kind of like what I would recommend. And it kind of follows the outline of a lot of colleges, I think, recommend you do. Obviously, every place is different, but whatever. I'm not going to repeat myself over and over. So the first thing here I would say is, what would I say? Probably like ordinary differential equations. Sometimes it's called DiffEq. And then I would pair it with elementary linear algebra. So ODEs is like, you have equations, but they have derivatives in them. So like maybe you have like y is equal to y prime. That's like a really basic example where you want to express y as a function of x. For what functions does that equation hold? You know, that's one of like the first equations that you come into. and you learn how to solve it and whatnot. And then elementary linear algebra is about, what's it about? That's like where you start doing, like you start playing with matrices. You talk about column rank and row rank, or I think it's just column rank. It's been a while since I've done elementary linear algebra. Solving systems of equations using matrices. Personally, I don't like matrices, so I never really much cared for it. It's okay. So after ODE, I've never taken this class, but I think PDEs is probably a good idea to take after it, because in ODEs, you're only doing like functions of one variable, whereas PDEs, you have functions of many variables. And you take partial derivatives. And then maybe here I would do math proofs. This class is called a number of different things. Math proofs. This class is the one that teaches you about logic. You can take a course that talks about this same stuff in different fields of study, like in computer science. You definitely need to take it. I think in computer science, at least where I went, it was called discrete structures. But it teaches you how to think. It's weird. It's a class in logic of how to, like, if-then statements. If this is true, then this is following it. And/or statements, how to negate statements, contrapositive, that type of stuff. Other places call it, I think, foundations of mathematics, but where I came from, it was just called math proofs. This was the math class that I had that made math difficult. Like all these other classes I took, none of them were I found super challenging. But math proofs was the one where I really had to study hard because I didn't understand how proofs worked. And it wasn't until like the fourth time around that I really started to understand it. Okay, so the year after that, so I use these brackets to denote like a year. So this is the first year, second year, third year. Although theoretically, you would take this stuff in high school, I think. So maybe like junior year, senior year, freshman in college, sophomore in college. I don't know, maybe I'm confused. You can start this whenever you want, This is more like if you want to do this yourself and you want to know where to, basically get an outline of what you should do or what I should do. I mean, this is what makes sense to me, is all I'm saying. Okay, so what comes next? So at this point, once you've had math proofs, I think it's probably a good idea to get into like modern algebra and analysis. However, it kind of, I don't know, it's, at this point, math is not going to be, if you found this math easy, then this math is where it starts to get really challenging. So I'm going to call this first one elementary number theory. I've never actually taken a course in number theory. Well, I am this semester, but it's not the same as elementary number theory. I think where I went, we used to call it modern algebra, which is like, I have a reason for putting number theory here instead of calling it modern algebra, and you'll see later. But I'm going to put elementary number theory here. So, which I'm assuming is largely algebraic. And so 1 and 2, so that's first, second semester. And then we have real analysis. This is the undergraduate version. So that would be like something like in the Bartle book here that I mentioned the other day. So this is the type of book that you would study for that. And then the year after that, I think you get to play around a little bit with what you want to study. So let me think here. If you take this in college, then maybe this would be your freshman year, sophomore, junior, senior. So here you kind of get to play around, I think, with what subjects you want to study. So I think it would be a good idea to take like a class in complex analysis. We'll call it 1 and 2. You can take there's like a graduate school level version of it and an undergraduate level version of it. I think the sequence that I'm taking of this now is accessible to undergrad students. And it depends on what the instructor wants to do with it. I think the concepts that we learn in the grad school level are accessible to undergrads. So I'll put it there. And then for these two, I think you can play a little bit. So I would say that a course in advanced linear algebra would be useful. There is a really good book about advanced linear algebra. It's by Sheldon Axler, and the book is called, what's it called? A Linear Algebra Done Right. It's the book that I used when I took that course. And I think at first I struggled a lot with it because I didn't have the mathematical maturity. But I probably read through the book multiple times, and I wish I kept the book because the book is really good. And it avoids matrices. I think that's why I liked it. There are matrices in it. It's just that the focus isn't on it, I guess you could say. And then I would probably put geometry here. Geometry. Because I noticed through all of this, there's not really a designated geometry course. So I think a catch-all geometry should go here. You know, this you can talk about Euclidean geometry, which is what we're all familiar with in high school. But also talk about non-Euclidean geometry, which plays around with the fifth postulate, I believe, from Euclid. Okay, so did I miss anything? This is all pretty good if you can get through all of this. Like, you would probably, like, if you did all of this by yourself, you could probably have, like, an equivalence of a bachelor's degree in mathematics. You know, I say that with a lot of... I say that with a concerned look on my face, which you can't see because it's dangerous to say stuff like that. But I think this is pretty good, I guess. It depends on how much you want to do. So that would be like undergraduate studies. So what about grad school level studies? Well, if you're in pure math, like me, you can't get away with without abstract algebra. Abstract algebra. First and second semester. So this is the reason why I did not include modern algebra up here, because I'm kind of throwing in a lot of those undergrad level concepts into elementary number theory. And I'm saving all of the really algebraic stuff for this class because I think it fits better here. That's the only reason why I did that. So in abstract algebra, you pretty much always start with group theory. And you spend a good deal of time on group theory. I think the whole first semester here is group theory. And the second semester, you start to talk about ring theory. Maybe do like a third of the semester on ring theory. I don't know. It depends. Again, it's up to the instructor's discretion. But you do ring theory, and then you also do field theory. Typically in the second semester. And then pairing that, you have what I would recommend, and I'm kind of diverging from what other institutions do. But this was my recommendation. I would say functional analysis. What do I mean by functional analysis? I mean pretty much anything that you could read in the first 6 chapters of this Kolmogorov book. That's kind of what I have in mind when I write functional analysis. There's also a book by Kriesig called Functional Analysis. I think if you just read through that whole book, that would be how I would build this functional analysis course around. I think that's what I would suggest. I should probably give some book recommendations for this list, which I don't think I have time in this video, so I might address that in a future video. So anyway, I would say that'd be like a first year grad school level. But, you know, typically the school that you're going to go to is not going to do it this way. This is me freeballing it here. So what would I recommend in the next semester? Well, it kind of depends on what you want to do. If you want to get your PhD in algebra or analysis or some applied mathematics course. But if you are looking to get a degree in analysis, which is what I am, then you must take measure theory. And I separate measure theory into its own course because it's its own beast. And from my experience and from what I see other people that go through PhD programs, measure theory seems to be the one that students, like if you're like me, it's the one you struggle with the most. I don't know what it is about measure theory that makes it so painful, but it's the killer of all the ones I put on this list. And I've taken measure theory, 2, 3, maybe you could argue 4 times now. It's just, you have to see it over and over and over again. And then what do you supplement it with? It's kind of up to you. But I think a good thing to take would be one semester you could do algebraic number theory, which is like a more advanced version of the number theory course, just at the grad school level, but with an emphasis obviously on algebra. And then the next semester you can take analytic number theory. Still number theory, but you approach it from more of an analytic background. Surprise, surprise. And anything you take after this is really up to you. You know, by this point, really let's say this point. After this point down here, you pretty much can read any textbook you want. It may be difficult, but you can read it. So, other classes, I guess. So, other courses. I would recommend. I'm currently taking probability theory, which is an applied math course. It's very much in the neighborhood of measure theory. So my measure theory is carrying me through on this class. It's a good class, I would take it. This also depends on who teaches it, but my instructor is very, very, very good. Who else would go well with this? There's a course in potential theory that I took that I thought was pretty interesting. So that might be, it's like an extension of complex analysis. Trying to stay away from the applied math courses just because I don't want to comment on them because I haven't taken those classes, so I can't really recommend anything. There's statistics. There's numerical analysis. I'm kind of curious about that one, numerical analysis. That might be a good one. You could also probably take a course in graph theory. I have a book on graph theory, which I haven't read, but I've always been wanting to read it. And what else? What else? I mean, there should be like I wish there was more courses in geometry than there are. Feels like the road less traveled. I guess I'll just put statistics down here because I think it's statistics. There, I can spell. You know what? Let's try that again. Statistics. There. Again, it really depends on what you want to study. So if you want to study pure math with an emphasis and analysis, I think this would be a pretty good list. Because you still need the algebra, you know. And if you take other courses, it just, it enriches you and makes you, I think better. It's just any and all experience that you can get can help you with this. So those are my thoughts. Let me know if I've been confused here, but I think this list is somewhat good. So that's what I would recommend for undergraduates. This would be what I recommend for graduates. So start with these guys and then maybe focus on these later. But again, it's, at this point, it's really up to you. So let me know what you think of my recommendations. It's kind of, it's not that much different from what an actual university would require you to take. It's just that I decided to split up analysis into 3 pieces, which is what I don't know if that's the best thing to do, but I would do like undergraduate real analysis, which would be like the Bartle book. Functional analysis would be the Kriesig book. And for measure theory, I'd have to find a really good measure theory book, but I mean, this Whedon book would probably be good enough. And I think the Royden book also does a pretty good job. But there's probably a really good measure theory book out there that I haven't found that I would recommend. So yeah, let me know what you think.